Hello everyone, my name is Mauricio Morales-Beltran and I'm going to present our paper Hybrid Fabrication of Discrete Topology Optimized Structures using 3D Printing. The outcomes of topology optimization procedures are very often continuum systems. Using common 3D printers, we can fabricate these continuum systems at smaller scale. However, when we attempt to produce such systems at real or large scales, the power or the potential of these printers is limited. In our study, we explore what are the advantages and disadvantages of converting these continuum systems into discrete ones using hybrid fabrication, which is a combination of 3D printed nodes with conventionally built timber or steel bars. The procedure starts in MATLAB, where we use script developed by Liu and Tovar in 2014 to produce a continuum system. This continuum system can be manipulated based on parameters such as the size of the three-dimensional design domain and the target volume fractions. Once the topology optimization is accepted, MATLAB is going to export the matrix as an Excel file. Once in Grasshopper, the algorithm is going to read this Excel file in order to produce an equivalent system based on several cubes representing these finite element array. However, these boxes or cubes are not connected to each other in Grasshopper, so we are going to use first a plugin called Metaball Point Charge to produce a force field at the center of each of these boxes. Then a plugin Cocoon is going to connect these force fields to create a continuous mesh, polygonal mesh. And finally, a plugin called Dendro is going to control how smooth this mesh is going to be. Once this mesh is accepted, we need to proceed with the subdivision of this design into discrete elements. Once this discrete array is accepted, we need to proceed with the computation of the radius of gyration. Why radius of gyration? Because these new discrete systems are going to resemble either truss or frame configurations. In the former, we have configurations where the members are experimenting either tensile or compressive stress. Therefore, buckling resistant capacity is required. And in the frame systems, the nodes experience bending moment, and they are going to require some flexural capacity in the bars as well. So the radius of gyration is the relationship between this bending resistant moment of inertia and the axial strain provided by the cross-sectional area of each bar. So we take some sections from each bar. We calculate the actual radius of gyration of each of these sections. And then we convert that irregular section into regular ones. This could be a square or a circular one, depending on what is our target as regular bar. Once this regular bar section is accepted, we need to proceed with the design of the connections. In order to design the connections, we need to answer some questions. What type of anchorage system are we going to use? What type of materials are we going to use, and how we are going to ensure that the stiffness is homogeneously distributed in these new 3D printed pieces? and actually how we're going to make the connection between bars and nodes. In order to answer some of these questions, we first test the anchor system using two approaches, one with only screws and the other one adding some plastic anchor. Both of these solutions provide a reliable alternative for making the connections. However, we also test one using cartridge, which turned out to be very unreliable, basically due to the fabrication process, which produced some uneven connections. For the experimental testing of cylinders of 10 centimeters diameter and 20 centimeters long, we use 45% gyro infill with different filaments. The results of this test show that the PLA specimens tend to collapse due to buckling, whereas the PETG specimens are a little bit more stable, especially in the post-yielding behavior. However, they also buckle very often, and let's say the best performance was obtained by those specimens made out of PLA plus, which displayed a very consistent behavior. Simultaneously, we design and fabricate our first PLA prototype in order to study how we can connect bars and nodes. So this first connection had 6 bolts, and the problem with that is that the resulting model was quite heavy. So an upgraded version, the size of these connections were reduced, and the number of bolts used was half of the original one. This significantly reduced the total weight of the structure. The final prototype was a hybrid combination of timber battens and PETG nodes. In order to connect these buttons with the node, we use that element that is in blue in the picture, which is glued to the timber button, and then is screwed to the connection in order to transfer the bending moment. To finalize, what we learn in terms of methodology is that the algorithm sometimes produce asymmetrical distribution of material, so that needs to be fixed in future versions of these methods. On the positive side, focusing on the radius of gyration allows the algorithm to convert this continuous system into virtually any possible discrete system based on regular bars. From the experiments, what we learned is that controlling the printing parameters is key to obtain stronger connections. However, the open question here is whether these connections should have the same strength of the bar, or should be stronger, or should be weaker. That is our presentation. Thank you very much.